Today, we are talking about the rules of probability. First, let's talk about the fundamental rules. If an experiment has an equally likely outcomes, the probability of each outcome is 1 over n. Now, for any event E, 3 rules always apply. First, probability is always between 0 and 1. Second, the probability of an impossible event is 0. Third, the probability of the entire sample space is always 1. And if events are mutually exclusive, meaning they cannot happen at the same time, you simply add their probabilities together. Now, if an experiment can result in any one of indifferent equally likely outcomes, and exactly n of those outcomes correspond to event E, then the probability of event E equals n over n. This is the basic formula we will be using throughout this lesson. Now let's talk about the additive rule. If A and B are any two events, then the probability of a union B equals the probability of A plus the probability of B minus the probability of A intersection B. Why do we subtract the intersection? Because if we just added the probability of A and the probability of B, we would be counting the overlap twice. Think of a Venn diagram. The middle part belongs to both A and B, so we subtract it once to avoid double counting. Let's work through a real example. In an engineering college graduating class of 100 students, 54 studied calculus, 69 studied engineering data analysis, and 35 studied both calculus and engineering data analysis. If one of these students is selected at random, find the probability that Part A, the student took calculus or engineering data analysis. Part B, the student did not take either of these subjects. And Part C, the student took engineering data analysis but not calculus. Now let's solve each part. Consider the events. A is the event that the student took calculus. B is the event that the student took engineering data analysis. Part A, the probability of a union B equals 54 over 100 plus 69 over 100, minus 35 over 100, which equals 22 over 25. Part B, the probability of the complement of a union B equals 1 minus the probability of a union B, which equals 1 minus 22 over 25, which equals 3 over 25. Part C, the probability of a complement intersection B equals the probability of B minus the probability of A intersection B, which equals 69 over 100 minus 35 over 100, which equals 17 over 50. Each part uses a different version of the same formula. Let us solve this using a Venn diagram. We have two sets, A for calculus and B for engineering data analysis. For set A only, we compute 54 minus 35, which equals 19 for set B only. We compute 69 minus 35, which equals 34. Now the intersection of A and B, meaning students who took both subjects, is 35. To find the number of students who took neither subject, we compute 100 minus 19 minus 35 minus 34, which equals 12 for part A. A union B equals 19 plus 35 plus 34, which equals 88. Therefore, the probability of a union B equals 88 over 100, which simplifies to 22 over 25. For part B, the complement of a union B equals 1 minus 88 over 100, which equals 3 over 25. For part C, the probability of a complement intersect B equals 34 over 100, which simplifies to 17 over 50. Here is our second example. If each coded item in a catalog begins with 3 distinct letters followed by 4 distinct non-zero digits, find the probability of randomly selecting one of these coded items with the first letter being a vowel and the last digit being even. Let's solve this. The total number of codes n equals 26 times 25 times 24 times 9 times 8 times 7 times 6, which equals 47,174,400. This is because there are 26 alphabets. After using 1, it becomes 25, then 24. This is because the letters are distinct. Also, there are 9 non-zero digits, which are 1 through 9, so we have 9 choices first. Then 8, then 7, then 6, since we only need for digits. The digits are also distinct or non-repeating. Now for the favorable outcomes. The first letter must be a vowel, so we have 5 choices. After using one of the 5 vowels, we have 25 alphabets left, then 24. For the digits, after using one of the 4 even digits for the last position, we have 8 choices left for the first digit, then 7, then 6. So n equals 5 times 25 times 24 times 8 times 7 times 6 times 4, which equals 4,032,000. Therefore, the probability is n over n, which is 4,032,000 over 47,174,400, which equals 10 over 117. For the last example, in a poker hand consisting of 5 cards, find the probability of holding, part A, 3 aces, part B, 4 hearts and 1 club. Let's solve each part. Part A, we need to choose 3 aces from the 4 available aces in the deck, and 2 other cards from the remaining 48 cards, the combination of 4 taken 3 at a time, multiplied by the combination of 48 taken 2 at a time, divided by the combination of 50 to taken 5 at a time, equals 94 over 54,145. Part B, we need to choose for hearts from the 13 hearts in the deck, and 1 club from the 13 clubs in the deck, the combination of 13 taken 4 at a time, multiplied by the combination of 13 taken 1 at a time, divided by the combination of 50 to taken 5 at a time, equals 143 over 39,984. This is where combinations are powerful. They let us count specific outcomes out of millions of possibilities. If this helped you, like and subscribe for more math lessons. Drop your questions in the comments. See you in the next one.